In this video, we are working with section 11 for the binomial theorem. So the binomial theorem is a theorem we're developing so that we can expand binomials, among other things. But generally, to start with, we're going to be using it to expand binomials. So if we have this binomial x plus y, and we're raising that whole thing to the 0 power, what would that be worth? Or what would that value be? All right, so that's going to be 1, because anything raised to the 0 power is 1. All right, so pretty quickly we can see that if we take that same binomial x plus y and raise it to the first power, we know that that's going to be just x plus y. But bear with me for a minute, and indulge me here. I'm going to include the leading coefficients. So we have 1 x, and then another thing I want you to do is, when you're doing this in this particular portion, always include the exponent on the variable. So in this case, it's going to be 1, which normally we wouldn't include, x to the, and then we also probably wouldn't normally include the 1, but I'm going to here, plus 1, and then y to the 1. Okay, so try when you're writing these out also to keep them all centered. It'll make sense why in a minute when we come over to this and we use the Pascal's triangle. All right, so now let's go down to the next one, squared. Now most of you probably can do that in your head. We should be able to take a binomial and square it without actually foiling it out. And so we'll do 1. That's generally we would say just x squared, but again, include the coefficients on every term. Bear with me, it'll make sense in a second. So it's 1x squared plus 2x, again, to the 1, y to the 1, and then plus 1y squared. Okay, so again, normally we wouldn't really include the exponents here on the 1 exponents, and we wouldn't include the 1 coefficients, but we're going to here, and it'll make sense why in a minute. Okay, so now what I'd like you to do is try to get, expand this one out. So this is the binomial x plus y cubed. So most of you probably can't just write this out. You'd have to write out those two binomials. So you'd have to do something like x plus y times x plus y times x plus y. Foil these out, and then take this and foil this, or multiply this binomial by the resulting trinomial that we would get, which we know is the same thing as this up here. So take a second and do that. All right, so the resulting answer here then, again, I'm going to include all my coefficients and all my exponents. X cubed plus 3x squared y plus 3x to the 1 y squared plus 1y cubed. Okay, now what I would like you to try to do is come up with what you think the next thing is going to be without foiling it all out, without multiplying all these binomials together. Just by looking at the pattern that you see here, see if you can come up with what the expansion of this binomial to the 4th power would be. All right, so here is the result if we were to expand this out. Now, it might be even more helpful to do the following. Write this as 1x to the 4th y to the 0 plus 4x cubed y to the 1 plus 6x squared y squared plus 4x to the 1 y to the 3rd plus 1x to the 0 y to the 4th. So you can see I've added these extra terms of y to the 0 here, which we know is just 1. We normally wouldn't include that. And at the last term, x to the 0, which we would not include in our final answer, but I'm doing it here just to demonstrate the pattern here. So notice, first of all, when we have a degree 4 that we're raising it to, how many terms do we have? We have 1, 2, 3, 4, 5, right? So we're going to have one more term than the degree that we're raising the binomial to. All right, also notice that the x's, the exponent on the x's, start at 4 and go down by 1 with every term. So we have x squared, x cubed, x to the second, x to the first, and x to the 0. So that's why I included the 0, so you could just see that pattern. Now the y exponents, or exponents on the y, do the exact reverse. They start with 0, which we normally don't write. Again, y to the 0. That would, not be a good thing to leave your answer in. We'll just ignore that and make it a 1. So we have y to the 0, and now it increases by 1, y to the 1, y to the 2, y to the third, y to the fourth. So the exponents on the two variables increase. One's increasing by 1 and one's decreasing by 1 as we go across. All right, so now let's concentrate on the numbers. So 1, 4, 6, 4, 4. How did we get those numbers? And if you did, hopefully you saw the pattern here, how we got these. So we have a triangle, and you notice the triangles start with 1. So like we could think of it here. We have 1, and we have 1 and 1. Each row starts and ends with a 1. So this one represents this one, right? The 0th row, if you want to think of it, the 0 row. The row with a 1, or the first row then, is 1, 1. The next row, we're looking at just the coefficients. So this is going to be a 1, 2, 1. This is the row, the second row, with the index, with the exponent of 2. The third row is just going to be 1, 3, 3, 1. And so now what we want to think about is how we could get these 5 numbers. Remember, it's degree 4, so there's going to be 5 terms, 5 coefficients for the 5 different terms. How can we get those numbers from these? Well, again, we start with 1 always, we end with 1 always. And then how would I get this 4? Well, this 4 is gotten by just adding the 2 numbers diagonally. So the 4 is kind of in between but below the 1 and the 3. So we add the 1 and 3 up and get 4. And there's a symmetry, so this one's also a 4. But in between here, we get a 6. All right. So without actually doing these, x plus y to the 5th, you should be able to come up with what goes in the rest of that Pascal's triangle. So let's do that. So we do 1. So you just have to kind of keep your spacing accurate here, consistent, and just try not to make your numbers too big. Remember, they got to stay right in the middle between these two. So this is going to be a 5, and a 10, and a 10, and a 5, and a 1. And you can see there's a symmetry here as well, right? And so this would be the 5th row. This would correspond to some binomial raised to the 5th power, all right? So that first non-1 number tells us what the exponent on the binomial is. So this will give us the coefficients of the terms of the binomial expansion that's being raised to the 5th power. And then if we want to raise to the 6th power, we keep adding. So in other words, we just keep putting new rows in. So these 2 will add up and give me a 6. These 2 add up and give me a 15. These 2 add up and give me a 20, 15, 6, and 1. Okay? So this would be if I took a binomial and raised it to the 6th power. These would be the coefficients. Now, it's not always the final coefficients, but it's the starting point. And we'll talk about that when we do example 2 down here. All right, and then let's go down because we're going to need row 8. So let's go down to row 8. So this will be 1, 7, 21, 35. Again, careful your spacing, 35, 21, 7, and 1. Now I know because there's an 8 down here in example 2 that I know I'm going to want my 8th row. So let's do that. That's going to be 1, 8, 28, 56. Again, I got to be careful of my spacing so I don't make the numbers too big so they don't fit. 70, and of course now we start back over again. It's a symmetrical, so 56, 28, 8, and 1. Okay, so we're going to use this to expand some of our, expand this binomial, raise it to the 6th power. So try that right now. Try expanding that out. All right, so I know my coefficients. I'm going to look at my row here. I'm going to do a 1. And then the first thing, x to the 6th power. If I wanted to, I could do y to the 0. I'm going to eliminate that eventually, so that we should not have that in our final answer. So I'm just going to leave it off now. But just know that that would be sort of like a y to the 0 there. All right, and then plus 6. X decreases by 1. Y increases by 1. And again, I could just write y, but I'm going to do it with my exponent so you can see the pattern. And then plus 15, x to the 4th, y to the 2nd, plus 20, x to the 3rd, y to the 3rd, plus 15, x to the 2nd, y to the 4th, plus 6, x to the 1 if you want, y to the 5th, and then finally 1, y to the 6th. X to the 0 could be put in there, but we don't really need it, so that's a plus sign. Okay, so you can see if you had put the zeros in, you really want to get rid of those. You don't really need this 1. You could have left it off. You could have left this 1 off, but you can see the pattern sort of is nice. Also notice that the exponents, the sum of the exponents in any one of the terms should equal the original exponent on the binomial. So these two add up to 6, and it's a good check just to check those. If any of them don't add up to 6, then you did something wrong. Okay, so try the next one. In this case, maybe start down here. This one's going to be pretty long. You might run out of space if you are writing kind of big. So write sort of small, and so try number 2. Okay, so in this example, we're going to use these coefficients. These are the coefficients. Now, because one of our terms is not strictly a variable, it has some numbers in it, these coefficients will not be the final coefficients like they were here, right? So in the row 6, we just use those as the coefficients, and that's what they were. Here, we're going to have a little bit of change because there's a 2 in here. So just be careful. All right, so we're going to do 1 y to the 8th, and then the other term, which is 2 to the 0, which I'm just going to leave off. All right, plus the next term is 8, so 8 y to the 7th, 2 to the 1. So you can see where I'm going to have to come back and fix this because I know this coefficient looks like 8 to start with, but I'm multiplying it by 2 in the next step. It'll be 16. So, and then let's continue. Plus, then the next one is 28. Y to the 6th, 2 to the 2nd, plus 56. Y to the 5th, 1 less, 2 to 1 more, the 3rd, plus 70. Y to the 4th, 2 to the 4th, and again, you can double check. These two numbers, right? In each case, the two exponents in each term should add up to our 8, and they do. So, it's a good check as you're doing this. 56, y to the 3rd, 2 to the 5th, plus 28, y to the 2nd, 2 to the 6th, plus 8, y to the 1, 2 to the 7th, and then finally, the last one is going to just be 1. If I wanted to, I could say y to the 0, or then 1 coefficient times 2 to the 8th. Now, we need to go back and write a final answer. We need to simplify all these things. And And so then we have what? So let's put equal signs in here. And so you have to be careful too. Like this is 9 terms. If you wrote it a little bit too big, you may not have fit it. But it's good to try to write a little bit smaller so that you can fit it all in one row. Otherwise, you're coming down to another line and it gets a little confusing. So just try to be conscious of the fact that you got to write a little bit smaller with some of these. All right, so I'm going to say this is just y to the 8th. I'm not going to leave that coefficient of 1 off. I mean, I could leave it, but just normal to not write it because you don't really need it. And then plus 16y to the 7th. So I got to multiply these two together. This is one term. The numbers all become the coefficient out in front. All right, and so the next one, this will be 112 y to the 6th. So that's 28 times 4, 112. And then the next one is going to be 448 y to the 5th. This is going to be what? 8 times 56, which is 448 y to the 5th. Okay. And then the next one is going to be 70 times 16. That's 1,120 y to the 4th. All right, then plus, now there's symmetry here, but there's not symmetry going to be with these numbers because my 2 just keeps getting bigger, right? My 2, exponent on my 2, so 2 to the 5th is going to be much bigger. So you're not going to see the symmetry that you normally would here. All right, so 56 times 32, in this case, 179, 1,792 y to the 3rd. And then the next one, coincidentally, happens to be the same coefficient, 1792 y squared plus 1,024 is 2 to the 7th times 8, and then that's just y, and then finally 2 to the 8th is 256. All right? So try the next one. It's a little bit trickier. It'd probably be helpful if you think of this not as x minus 3, but x plus a negative 3. The negative has got to be part of the thing that's being raised to the power every time. So try that one. We'll be using this row up here, right? Because it's this row is raised to the 5th power. So try that one. All right, so I'm going to start with the 1, x to the 5th, and then plus 5, x to the 4th, and negative 3 to the 1. Next term is 10, x to the 3rd, negative 3 to the 2, plus another 10, x squared, negative 3 to the 3rd, plus 5, x to the 1, negative 3 to the 4th, and then finally 1, x to the 0, if you will, negative 3 to the 5th. Now we need to take that and expand it. Multiply the numbers together to get our real coefficients out in front. So that ends up being, and I'm going to get rid of the 1, I'm just going to say x to the 5th. Now, in this case, this will be negative because it's being raised to the odd power times a positive. So I know this is going to be negative, and 5 times 3 is 15 x to the 4th. Okay? The next one I know is going to be positive, and indeed these are going to alternate because this negative is being raised to an odd power, then an even power, then an odd power, then an even power. So the signs of my terms will alternate between positive and negative. All right, in this case, this is a 9 times a 10, so that's 90, x cubed. I know the next one's going to be negative. This is negative 27. Times 10, so that's subtracting 270, x squared. All right, and then I've got 81, and it's positive, so it's plus 81 times 5, 405, x to the 1. And then finally, it's going to be negative, and this is just 3 to the 5th is 243. All right, so just notice in this last example, we only had one variable. It's because we only had one variable. One of our terms had a variable in it. Same thing with example 2, it only had y. So we didn't have two variables in each term, we only had one. Here we had an x and a y. So again, every term had x's and y's. Well, except for the first and the last, I guess. Okay.